Hey everyone! So, today is our last chapter, chapter 17, which is over thermodynamics. Now, previously in the year, we talked about something called thermochemistry, where thermodynamics is just kind of the applications of thermochemistry. So, in thermochemistry, we talked about QSMAT, we talked about enthalpy, we talked about the changes or transfers of heat. Well, in thermodynamics, we are going to bring up enthalpy again, but we're also going to talk about things like entropy, which is pretty much chaos. And we're also going to talk about Gibbs free energy some more and why reactions are favored at certain temperatures. So we're going to talk about that today. So make sure that you're paying attention because we're covering this whole chapter just in one lesson. So the first thing is, what is thermodynamics or chemical thermodynamics? Well, chemical thermodynamics answers the question of why does a reaction occur? Okay, so thermodynamics answers the question of why does a reaction occur? And it turns out that it's really two main influences that drive a reaction. And that first one is one that we've talked about already, which is change in enthalpy, which, as you know, is shown as the sign of delta H, okay? So change in enthalpy is a big driver. Heat is transferred or absorbed by the surroundings, right? They're either exothermic or endothermic, okay? Typically reactions like an exothermic reaction, they like to release energy. So that's a driving force. And the second one is a change in entropy, okay? Change in entropy, which we're going to talk about in a little bit here. But what it's denoted as is delta S. So enthalpy and entropy, you'll hear me say those. Yes, they're very similar, but please know the difference. Enthalpy is the change in heat, whereas entropy is that delta S, which is pretty much known as randomness or disorder, okay? The common definition that people love to use for entropy is randomness, disorder. But what I want you to think of with entropy is how spread out things are, okay? The more spread out molecules are, the more entropy there is, the more disorder, if you wish. Okay, but let's start thinking about how molecules are maybe more spread out. That means they have a higher entropy. And if they're closer together, that means they have a low entropy. All right? So, again, we got enthalpy and we have entropy. And here's the thing about enthalpy and entropy. Chemical systems prefer a low enthalpy. Okay, so that's something like a negative delta H, which we know is exothermic. So reactions like to release heat. Okay, that just leads to more disorder. And it also prefers a high entropy. And in our case, a high entropy means a positive delta S, okay? So it likes more disorder. So reactions like there to be chaos. They like to be spread out from each other if they can. They like to release heat if they can. Let's always remember that. We want a negative delta H and a positive delta S. And what you're going to be hearing from me is when we have a positive S and a negative delta H, as you'll hear me say a spontaneous process. Spontaneous process, which means essentially the reaction will happen on its own. There's no drive needed. Okay, so there are some reactions that we need help to get started, like to light a lighter for gasoline in order for it to combust. Okay, it just doesn't combust on its own at room temperature. Sometimes we need a battery to get a reaction going, right? To transfer electrons. Sometimes we need a battery. Some reactions are spontaneous, okay? When you put a salt in water, it's going to dissolve on its own. That is a spontaneous reaction. You don't have to do anything to make that happen, okay? So spontaneous process is the reaction will happen on its own, but I won't be using the term spontaneous because the College Board does not like that word. What they prefer is the word, instead of spontaneous, is thermodynamically favored. And you've talked about this, or we've talked about this before. So when you hear me say thermodynamically favored, that means it's spontaneous. It will happen on its own. So when it has that negative delta H and that positive delta S, that means that we like a thermodynamically favored reaction, okay? So just a reminder, a little bit about enthalpy some more, okay? Enthalpy, remember, is delta H. Remember, when it is negative delta H, that means it is a exothermic reaction, and it is thermodynamically favored, right, or spontaneous, but we're not using that word spontaneous, we're using thermodynamically favored. And then if it's a positive one, it's endothermic. And if you remember from our thermochemistry chapter, the delta H of a reaction equaled the H of the products minus the H of the reactants, right? So I was giving you some enthalpies for the products and the reactants. You just take the enthalpy of those products, subtract the enthalpy of the reactants, and it'll give you the whole enthalpy of the entire reaction. That's important because it helps us also with entropy as well. So just remember, thermodynamically favored means spontaneous. The reaction happens on its own. We like negative H, we like positive S. And here's some review things from enthalpy. Remember, negative is thermodynamically favored. It means it's exothermic, heat is being released. Positive delta H means it's endothermic, it's being absorbed. And we can always find the total enthalpy of a reaction by taking the enthalpy of the products minus the enthalpy of the reactants. Let's go ahead now and let's talk some more about that delta H, or that delta S, or that entropy. So entropy, like I said before, you kind of think of it as randomness or disorder. Entropy just means more randomness or more spread out, okay? So some examples of this where entropy is higher is gases have more entropy than liquids. A lot more, right? Gases fill the room. Right now, there's tons of gas surrounding me, right? It is all over the place. It is a lot spread out. But if I put liquid water in a glass, right, it's not very spread out. It's got a very, very low entropy. Okay, so gas has a huge amount of entropy. Liquid, not so much. But that being said, liquid does have more entropy than solids. Okay, gases, the difference from gases to liquids is huge, right? Gases are all over the place. The difference between liquid and solid, it's not much different in terms of entropy. Yeah, liquid is a little bit more spread out, right? Those water molecules can move freely a little bit more, but it's not as huge as that difference from gases to liquid. So keep that in mind, okay? Just know that gases have a huge amount of entropy compared to that of liquids and solids. Some examples. So again, if a gas has more entropy, okay, it means it has a positive S. So if we have a situation where we have a liquid going to a gas, that means we have a positive entropy. There's more disorder. That's what we like. We like a negative H and a positive S. If, let's say, a liquid goes to a solid, that's less entropy. We don't like that. That's a negative S. Okay, negative S. So keep that in mind. Some examples of increased entropy. Okay, it happens a lot more frequently than you think. Examples of increased entropy or more disorder or more spread outness, right? Examples where molecules will spread out more, okay? Or positive S, right? Examples of this are a like I said before, a liquid to gas, that is an increase in entropy. That's a positive S. A solid to a liquid or gas, that is also a positive S, right? These are all increases. Another one that we haven't talked about is when temperature increases, right? When we increase the temperature, that means that those molecules are going to speed up. They're going to spread out more. So that's an increase in entropy. And then when you start thinking about temperature increases, you can start thinking about volume increases and maybe pressure decreases, right? So we have volume increase, right? If the container gets bigger, the molecules are going to spread out more. So that's another increase in entropy or disorder. Okay, here's another one. Particles increase. And what do I mean by particles increase, right? You might be thinking of a single particle getting bigger and bigger and bigger. That's not what I mean. I mean like taking a particle and breaking it up into smaller bits. Example of this might just be crushing a rock. Or what I like to do when I go to the beach, right, is find those clumps of sand and then it looks like a rock and you crush it and you feel super strong. Okay, I don't know why I'm saying this, but you know what I mean. That's an increase in entropy. We're creating more particles. We're taking that chunk of sand that looks like a rock, we're crushing it, making us feel strong, but it's also creating a bunch more particles, or it's increasing our entropy. And the last one that the AP likes to bring up is dissolving a solid, okay? Like putting a solid into water, right? You're breaking up those molecules. Like if you put salt in there, it's no longer NaCl, it's Na plus and Cl minus, and they're getting away from each other. That is an increase in entropy as well. So always consider this when thinking about entropy. AP exam likes to ask you a bunch of conceptual questions about entropy, and they'll ask you, is entropy positive or negative here? Well, if there's more disorder or more randomness or more spread outness, it's positive S. That's an increase in entropy. Okay, let's talk about a couple of definitions that we need to know about, okay? Such as just a few definitions, and that is the second law of thermodynamics, which is just stating that the universe is constantly increasing in disorder, right? We said that when volume increases, entropy increases. Well, the universe is always expanding, right? We're seeing a bunch of galaxies that are redshifting. That means they're getting further away from us. The majority of galaxies are like that, so we're saying that the universe is expanding. Okay, so entropy is increasing all the time in our universe. And then we gotta talk about the third law of thermodynamics. I'm not gonna write of thermodynamics. Okay, this is just a random tidbit that they want you to know. The entropy of a perfect crystal at 0 degrees Kelvin is 0. Okay, so this just means, let me not write the number 0, let me write actual 0. Okay, so that just means a perfect crystal means the molecules are perfectly compacted together as much as they can. There's no such thing as a perfect crystal, it's all theoretical. And then at 0 degrees Kelvin, right, that means those molecules are not moving whatsoever. That means the disorder is 0. Those guys cannot get compacted anymore. They're not going to spread out anymore either. Just something to note, okay? Always a good little, I don't know, factoid to know. Share it with your family and friends. I'd love to hear you define a perfect crystal. Okay, so those are our 2 laws of thermodynamics that we care about. Let's go ahead and let's do a couple examples. Let's predict if entropy is positive or negative. I'm running out of room. Oh, just made it. So let's predict if entropy is positive or negative. For A, let's go with solid sugar is added to water. Okay, solid sugar is added to water. Well, what's happening there when we add a solid to water, it's going to dissolve, it's going to spread out more, it's going to have more entropy, right? So that's going to be positive. Let's go ahead to B. Let's say iodine vapor condenses on a cold surface. Okay? Well, iodine vapor is condensing on a cold surface. Vapor is a gas, right? When it condenses, it turns into a liquid. So when it's going from a gas to a liquid, they're getting closer together. That's a decrease in disorder, right? That's a negative. That's something we don't like, right? That's something that's not thermodynamically favored. Okay, and let's just do one more. Let's say we decrease outside pressure on a balloon. So say we're taking a balloon from North Carolina all the way to Colorado to the top of a mountain. We're decreasing the pressure. That should increase disorder, right? If we're decreasing the pressure on the outside of a balloon, that balloon's going to expand more, right? Increased volume means more entropy, more disorder, more spread out molecules, right? And now one more thing we got to talk about, okay? Relating back to that delta H, remember delta H was H products minus H reactants. And this was actually in units of kilojoules per mole, right? Well, it's the same thing for delta S, right? Delta S of the whole reaction is entropy of the products minus entropy of the reactants. That is super, super, super nice. But the units are different, okay? So same type of equation, but the units are different. It is joules per mole Kelvin. So we're getting temperature involved in there, okay? It's not kilojoules per mole, it's joules per mole. And that will come in handy later on. So let's go ahead and let's do a calculation where we're using that new equation down there. So our first example here, it says calculate the entropy for sulfur dioxide reacting with oxygen gas and making sulfur trioxide. And I have given you the individual entropies for each of those reactants and products. So pretty much what we have here is just if we want to find delta S for the whole reaction, we just take the S of our products minus the S of our reactants. And this is on your formula sheet, your equation sheet. So this is pretty easy, right? We're just going to take the entropy of our products, which are, we'll have 2 SO3s, which is 256.6, and subtract the S of our reactants. We have 2 SO2s, so we're going to have 2 times 248 plus 1, and we're going to have the entropy of oxygen, which is 205.3. Right, if we plug that into our calculator, we should get something like negative 188.3 joules per moles Kelvin. Okay. So is this an increase or a decrease in disorder? Well, it's negative, right? If it's negative, we're going to see a decrease in disorder. Okay, not an increase, right? And that makes sense because we have 3 particles becoming 2 particles, right? That's less disorder. That's more or less chemicals in a container. So this makes sense, right? We solve for entropy. We look at this, it says, yeah, the entropy should go down there, right? We're getting less particles, less spread outness, and it shows up in our calculation. Okay, now let's talk again about Gibbs free energy. Okay, so here is Gibbs free energy again. Remember, Gibbs free energy is just the available useful work that we could have available for a reaction. And that is given by delta G. Now we had an equation where it was delta G relating to cell potential, right? E not. So it was delta G equals negative NFE. And then we also had rat link, right? Delta G equals negative rat link. Well, now we got a third Gibbs free energy equation, and this helps us relate that enthalpy and entropy. So the equation is our enthalpy is going to be our change in enthalpy minus our temperature times change in entropy will equal our delta G. So now we are relating delta G, delta H, and delta T. So let's write all three of these down. Delta G, okay, is available useful work or change in useful work. And its units are the same as enthalpies. It's kilojoules per mole. Okay? It's kilojoules per mole. Delta H, right, is the change in enthalpy, or the change in temperature moving around. Okay? Or of heat moving around, I shouldn't say temperature. Change in enthalpy, and it is kilojoules per mole. And then, again, we have delta S, which is change in, we'll say, randomness. And it's the only one that's got a different unit, which is joules per mole Kelvin. So, as you can see, and then T, of course, I guess I should define that, is temperature, and it will be in Kelvin. So, as you can see, we got to make sure that when we plug it into our overall equation here that we have everything in the correct unit. So make sure temperature is in Kelvin, make sure these two are in kilojoules, and then when we plug in S into this equation, we're going to have to convert this to kilojoules as well. So that's moving that decimal to the left 3. So that's an important step, is changing this to kilojoules when we plug it into that top equation. Okay? One last thing I want to mention here is just when these are spontaneous and not spontaneous. Okay? So this is based on sign. So when delta G is negative, it is spontaneous or thermodynamically favored. When it is positive, it is not thermodynamically favored, so it won't happen on its own. This is the same for enthalpy, right? We like it to be negative. So when delta G and delta H are negative, it is spontaneous or thermodynamically favored. Delta S is the opposite. It is thermodynamically favored when it is positive and when the other one is negative. And then E is the same as this order. Positive, it is spontaneous. Negative, it is not spontaneous. That's kind of good, okay? They're in pairs, right? And G and H are, A, B, C, D, E, F, G, H are right next to each other in the alphabet. So just remember, when both those are negative, they're thermodynamically favored. When they're spontaneous, they're not. And then S, E, okay? Those are the other pair. And they're thermodynamically favored when they're positive, not when they're negative. And one more thing about delta G, it's got kind of the same trend as our enthalpy and entropy, in that you could figure out the delta G also by taking the G of the products minus the G of the reactants. So let's go ahead and let's do an example where we're using this equation and our top delta G equation as well. So here is our first example. We want to calculate the free energy of this whole reaction, and here they have given us the delta G of each of our chemicals in our reaction. So again, this is just our standard reaction of delta G equals the G of products minus the G of reactants. So let's just go ahead and do this like what we did for delta H and delta S before so many times. So we're going to take the delta G of the products, which is 251.8 kilojoules of delta G minus the enthalpy of our reactants. Luckily, O2 is 0, so that's not going to affect it too much. But we do have two NOs at 86.7 kilojoules per mole. So let's go ahead and let's take 2 times 51.8 minus 2 times 86.7, and we should get a delta G of 69.8 kilojoules per mole. Okay, so is this going to be thermodynamically favored or unfavored? Well, delta G is negative, so this is thermodynamically favored. So this is thermodynamically favored. Thermodynamically favored, because it is negative, right? When delta G and delta H are negative, they're thermodynamically favored. When delta S and E are positive, they are thermodynamically favored. So we are good here. Let's do another example now where we're using that new equation of delta G equals delta H minus delta S T. So it wants us to calculate the free energy of this reaction up here. Okay, so free energy, remember, is delta G. So usually we could take products minus reactants, but they didn't give us delta G, right? They gave us delta H's and delta S's. So this is when that equation of delta G equals delta H minus T delta S, or HTAS, is a good time to use that equation there. So we got to figure out the delta H of this reaction, the delta S of this reaction. Well, they gave us the delta H's and delta S of all the products and reactants, so we're just going to use products minus reactants to find the overall delta H and the overall delta S, and then we can plug it into here with proper units to find delta G. So let's go ahead and let's focus on delta H first, right? Let's take the products minus reactants. We got two SO3s at delta H, so we'll do 2 times negative 396. And then we got our products, right? We got a 0 delta H for O2, but we got 2 SO2s at 293, or negative 297, sorry, delta H. So if we go ahead and we solve for that, our delta H is going to equal negative 198 kilojoules per mole. So we got our delta H, that's good. And that's thermodynamically favored because it's negative. Let's go ahead and find delta S. Our delta S is our products minus reactants once again. Well, our products for SO3 are 2 times 257, and our reactants are O2, which is 205, plus our other reactant, which is 2 times 248. So our delta S there is going to be negative 187 kilojoules per mole. Okay, to which you might be saying, Mr. Dahmer, this says it's thermodynamically favored. This says it's not thermodynamically favored, right? Doesn't delta S have to be positive? And also, sorry, this isn't kilojoules per mole, it's joules per moles degrees Kelvin, right? Remember, delta S has different units. But back to what I was saying, we have conflicting things here. This says it's thermodynamically favored, this says it's not. We'll talk about that later. When we have conflicting sign changes here telling us if it's thermodynamically favored or not, the thing that matters is the temperature, right? The temperature will help us determine if that's thermodynamically favored or not. Okay? So, once again, we got our delta H, we got our delta S. We need the temperature, right? Which is at 25 degrees Celsius, but we want that in Kelvin. So we'll do 25 plus 273 to get our temperature of 298 degrees Kelvin. Okay? So now that we got everything, let's go ahead and let's plug it into this equation to find delta G. So delta G is our delta H, which is negative 198 kilojoules per mole, minus our temperature, which is 298 Kelvin, times our entropy. But remember, our entropy has to be in the right units, right? This is in kilojoules. This likes to be in kilojoules. So our entropy also has to be in kilojoules. So to do that, we just move our decimal to the left, 3. So our delta S, let's go ahead and let's give me a little bit more room here. So it was negative 198 kilojoules per mole. Our temperature was 298 Kelvin. And now with our entropy in the proper units, it's negative 0.187 kilojoules per mole Kelvin. Kelvins cancel out. We're left with just kilojoules per mole. Okay, so again, make sure that that S is in the right units. So if we solve for delta G, our delta G is now negative 142 kilojoules per mole. And does that tell us it's thermodynamically favored? Yes. Okay. So overall, this reaction is thermodynamically favored, and we do that by basing it off of the delta G. So our delta H was thermodynamically favored, our delta S wasn't, but the temperature was high enough in order to make it thermodynamically favored overall thanks to that delta G. So we always look at delta G to determine overall if the reaction is thermodynamically favored or not. Okay? So let's go ahead and let's look at a table that helps explain that a little bit more. So the question I'm asking you is, when is delta G favored? So you saw in our previous example, we kind of had contradicting signs in our delta H and our delta S. Our delta H was negative, which is thermodynamically favored, and our delta S was negative, which is not thermodynamically favored. So that's where this equation comes into play, right? The thing that changes here is temperature, and that tells us if it's thermodynamically favored or not. And this table right here is something that the AP loves to ask questions about. So if we're looking at this first one, it says our delta H and our positive S is our signs. When is this thermodynamically favored? Well, remember, when delta H is negative, that's thermodynamically favored. And when positive S is around, that is also thermodynamically favored. So that will be thermodynamically favored at all temperatures, right? Remember, negative H minus a positive S will give us a negative delta G, which will always be thermodynamically favored, no matter what the temperature is. In this one, we have positive H, which is not favored, minus S, which is not favored, so it's not going to be favored at any temp, right? If this is positive and we subtract a negative delta S, it's always going to make our delta G positive, which is a not favored situation. And then we have these contradicting, I should say, signs, right? Enthalpy is positive, which is not favored. Delta or S is positive, which is favored. This will only actually happen at high temps. If the temperature is too low, it's not going to happen. If this happens at a high temperature, right, we'll get the negative S substantial enough to create a negative delta G value. And then with this negative H minus S, right, the enthalpy is good, the disorder is not, right? We got to have a high enthalpy, and it'll only stay negative if our temperature is low enough to keep that delta G negative, right? So if you think about it here, we need a higher temperature in order to make that enthalpy a little bit higher, and here we need a lower temperature in order to make that delta S not so effective, okay? So that is a table, explain all things. Let's do a little example here. What if we have a exothermic reaction, and let's say that we're going from a solid to a liquid. When is this thermodynamically favored? Well, if it's exothermic, our H is negative, right? And if we're going from a solid to a liquid, that means we're getting more disorder, right? Things are spreading out more, so our S is positive. Well, this happens at all temps. So it is thermodynamically favored at all temperatures. Let's do another one where instead, let's say that it's endothermic and it's going from a gas to a liquid. When is this thermodynamically favored? Well, endo is positive H, right? Gas to a liquid, that's less disorder, that's negative S. This is favored at no temps. Okay, so we don't like that either. And let's do one more down here at the bottom. Let's say that it is heat is being released. Heat is being released. And while this is happening, water is also freezing. So if heat is being released, that's a negative H, right? But if water is freezing, right, it's going from a liquid to solid, that means we got a negative S. Well, when is this reaction going to happen? It's only going to happen at low temps, right? That makes sense, right? To freeze water, you got to have a low temperature to happen. So if you want heat, if heat's being released and we want that water to freeze, we need to have a low temperature, okay? Guys, that is it for thermodynamics, okay? Make sure that you are using this equation to help you. You also might see a little bit of delta G equals negative rat link later on, okay? Again, it's just similar to what we've been doing. If you need delta H, you just take those products minus reactants. If you need delta S, products minus reactants. Make sure that you are knowing when it's thermodynamically favored and at what temperatures, and make sure you understand disorder, what makes it positive and what makes it negative. So that's it for thermodynamics. Let me know if you have any questions. Try out the practice below, and have yourselves a great day.